Imagine a future where the cracks in your smartphone screen vanish overnight, where roads quietly mend their potholes before your morning commute, and where airplanes in flight can patch their own microfractures without ever needing to land. It sounds like science fiction, but self-healing technology is no longer a fantasy. It is a field racing forward with materials that can repair themselves, inspired by biology and engineered at the molecular level. What does this mean for your daily life? Longer-lasting devices, safer travel, and infrastructure that feels almost alive in its resilience. Think of it as giving the world a nervous system and a skin that heals like our own. It's a world where objects don't just exist passively but actively defend themselves against decay, extending their usefulness far beyond our current expectations. But before we jump ahead, here's something to consider. The average American spends over $400 every 2 years replacing or repairing smartphones due to cracked screens. That's not just inconvenience, it's an entire industry built around failure. Repair shops, phone insurance, aftermarket parts, all of these exist because materials are fragile. If materials themselves could erase that damage, the economics of repair could shift entirely. Service shops would transform into diagnostic centers. Recycling systems could be redesigned to handle devices that last decades, and millions of devices might remain in circulation longer. The entire cycle of planned obsolescence could be upended, and that's only one of the countless ways self-healing tech might reshape the world. What's coming next could transform how we live, move, and build the future. Subscribe, like, and turn on notifications if you want to stay ahead of these breakthroughs. The story begins with self-repairing polymers. Think of them as plastics with memory. Unlike the rigid materials of the past, these advanced polymers have bonds that can break and reform, much like human skin closing a wound. One prototype polymer, tested at the University of Illinois, could restore 80 to 90% of its strength after being cut in half, without glue, welding, or human intervention. For smartphones, that means a shattered case or scuffed coating might knit itself back together in hours, not days. And when combined with advanced coatings like graphene, the potential for durability skyrockets. Imagine a phone case that looks brand new 5 years after purchase, or a laptop keyboard that resists years of typing wear by repairing itself overnight. In the near term, within the next 3 to 5 years, we're likely to see these materials integrated into consumer electronics. Why? Because companies like LG and Motorola have already experimented with self-healing smartphone backs. LG's G Flex phone, released in 2013, had a coating that could repair surface scratches in minutes. It wasn't perfect, but it was proof of concept. Since then, researchers have made the chemistry smarter, faster, and more efficient. Some polymers can now repair damage at room temperature with no external trigger. The bottleneck is cost. These coatings remain more expensive than traditional plastic, and consumer electronics margins are tight. But as production scales, the economics will tip. Imagine an iPhone that lasts twice as long or a smartwatch that shrugs off years of daily wear. The ripple effects would be enormous. Fewer devices discarded, less e-waste shipped overseas, and reduced strain on rare mineral supply chains. Now let's scale up to something bigger: roads. Globally, pothole damage costs drivers an estimated $300 billion annually. That's cracked rims, busted tires, and endless construction zones. Imagine instead a road that heals itself when rain seeps into cracks. Engineers in the Netherlands are testing asphalt mixed with tiny steel fibers. When the road begins to break down, a mobile induction machine passes overhead, heating the fibers and allowing the asphalt to flow back into place. Tests suggest this could double road lifespans from 10 years to 20, cutting infrastructure budgets in half. The concept works, but scaling it to millions of miles of roadway is an engineering and political challenge. Still, in pilot cities, the difference has been dramatic: fewer closures, lower costs, and smoother rides. And beyond asphalt, some engineers are experimenting with concrete that swells to fill cracks or mixes with bacteria that naturally produce sealing compounds. Take airplanes. Every flight subjects an aircraft to extreme stress. Pressure shifts, temperature swings, microfractures in metal. Typically, those fractures are invisible until they suddenly fail. Enter graphene-based coatings and polymer resins embedded with microcapsules. When a crack begins, those capsules rupture, releasing healing agents that flow into the fracture and harden, sealing the damage before it spreads. Airbus has invested heavily in this research, with the promise of reducing maintenance downtime by 50% and improving safety margins beyond current standards. The chemistry is ready, but aviation is conservative. New materials must endure years of rigorous safety testing before adoption. Imagine a future where inspections are not just reactive, but predictive, with materials that self-report and self-correct. Pilots could receive real-time data about structural health, and maintenance crews could spend more time upgrading planes than patching them. The everyday impact is enormous. If self-healing polymers and coatings enter consumer electronics, lifespans could double. That means fewer devices in landfills. E-waste currently totals 60 million metric tons per year globally, enough to cover Manhattan ankle deep. For roads, it means smoother commutes and billions in savings for governments and drivers. For aviation, it means safer skies and cheaper tickets, as airlines save billions on maintenance costs. And for industries like shipping, construction, and energy, downtime could drop dramatically. Oil pipelines could self-seal leaks before spills occur. Wind turbine blades could repair tiny fractures before they grow into catastrophic failures. Think about your own body. A small cut heals, bones knit back together. We don't call a construction crew every time we scrape a knee. Engineers are now asking, if biology does this, why can't our technology? That's where bio-inspired self-healing enters the story. The natural world is full of blueprints. Tree bark that seals, shells that regrow, skin that scars. Each provides a hint at how we might build structures that refuse to stay broken. If nature has already solved the problem of wear and tear, human engineering might only need to borrow and adapt those solutions. Now let's check hype versus reality. Self-healing is not magic. Many current prototypes require heat, light, or pressure to activate. Some heal only once, not repeatedly. Others take hours or days to restore full strength. Cost remains the single biggest blocker. Self-healing concrete, for example, can cost up to 50% more than standard concrete. Cities strapped for budgets often choose short-term savings over long-term resilience. Adoption will lag behind invention unless costs drop or incentives rise. Policymakers and insurers may play a critical role here, incentivizing longer-lasting infrastructure to avoid costly failures. Some governments are already considering tax credits for materials that extend lifespans, and insurance companies may one day offer lower premiums for buildings constructed with self-healing systems. Still, the future is full of possibilities. Consider bio-inspired structures. Researchers are studying sea cucumbers, whose skin shifts from soft to rigid, and lotus leaves which repel water. Imagine bridges or buildings designed with vascular-like networks that carry healing fluids, much like veins supply blood. One project in the UK demonstrated concrete infused with bacteria that secrete limestone when exposed to water, sealing cracks naturally. The bacteria can lie dormant for 200 years, longer than most human lifespans. The science is compelling, but scaling live biological agents into urban infrastructure raises ethical and engineering questions. Will the public accept a living building? Will cities embrace materials that act more like organisms than objects? These are not just technical issues, but cultural ones, redefining what it means for a structure to be alive. Here's a thought experiment. If roads and planes can heal, why stop there? Could entire cities become self-repairing organisms? Imagine skyscrapers that sense cracks forming and mend themselves before glass falls. Or spacecraft designed with materials that repair micrometeorite impacts in deep space. At that point, the line between biology and engineering blurs completely. A Martian colony might one day be built not of static steel and glass, but of materials that adapt, flex, and restore themselves like living tissue. A Martian colony might one day be built not of static steel and glass, but of materials that adapt, flex, and restore themselves like living tissue. Homes might breathe, factories might regenerate, and cities could evolve like ecosystems rather than crumble like machines. For consumers, this means less disruption. Think of the difference between replacing a light bulb versus living in a house where the walls patch themselves. Self-healing materials shift the paradigm from reactive to proactive maintenance. Instead of waiting for failure, objects continuously restore themselves, creating a silent, invisible safety net. Products might evolve from disposable goods to enduring companions, cars that never rust, clothes that reseal tears, shoes that regenerate soles. The very culture of consumption could change, with people buying fewer things but keeping them longer, supported by systems that keep them in prime condition. Now let's map out timelines clearly. In the next 5 years, we will see self-healing polymers in consumer goods, phone coatings, automotive paints, wearable devices. The chemistry works, and costs are slowly dropping. Expect premium devices and luxury cars to adopt these first, before mainstream rollout. Medical devices like implants and prosthetics may also see early adoption, reducing surgeries caused by wear. Infrastructure integration, roads with fiber-heated asphalt, bridges with bacteria-infused concrete, airplanes with microcapsule coatings. Field tests are underway, but regulation and scaling remain hurdles. Early adopters may include wealthy cities, national defense programs, and flagship airlines seeking competitive advantage. We may also see energy utilities experimenting with self-healing systems to prevent blackouts and minimize disaster recovery costs. The concepts are emerging, but real-world adoption will require breakthroughs in cost, regulation, and public trust. This era could see the rise of materials that behave less like machines and more like ecosystems. Buildings that adapt to weather, spacecraft that recover from deep space impacts, and vehicles that outlast generations. Think about how we used to view science fiction. In Star Trek, starships could repair themselves after battles, hull plating regenerating on command. Today, that concept is no longer fiction, it's a research agenda. The difference is that instead of futuristic shields, we're working with polymers, graphene, and engineered bacteria. The dream is the same, resilience that feels alive. And as AI begins to integrate with material science, we may one day see hybrid systems, materials that not only heal but learn, evolving strategies for resilience over time. If today we're making phones, planes, and roads that heal, what happens when the concept expands to the body itself? Researchers are already using similar principles in medicine. Hydrogels that repair damaged tissue, polymers that regrow spinal connections. Could the next frontier of self-healing technology merge our machines with our biology, creating a world where not just devices but humans themselves become self-restoring? Imagine artificial hearts that repair themselves, prosthetics that close microfractures, or even genetic engineering that gives us regenerative capacities beyond what nature provided. It's a vision where the line between repair and regeneration dissolves, and resilience becomes a fundamental trait of both technology and humanity. So, as we look ahead, remember, the promise of self-healing tech isn't just convenience. It's a radical rethinking of how we design for failure. Instead of planning for breakage, we plan for resilience. Instead of replacement, regeneration. And that shift could redefine technology in ways that ripple across every part of life. We are moving toward a reality where resilience is designed in, where failure becomes temporary, and where the world around us behaves more like a living system than a machine. The leap from reactive maintenance to proactive regeneration could mark one of the most profound shifts in human history. The self-healing future is closer than you think. To stay with us as we uncover the breakthroughs that are quietly reshaping tomorrow's world, subscribe, like, and turn on notifications. This is Tech Mythos.